Okay, we continue now. So now we are going to talk about infinite dimensional vector spaces. So what is called functional analysis. So let me change this and come to Banach spaces. So what are Banach spaces? A Banach space is a norm vector space which is complete. Remember, we just introduced the term completeness. So this means that in a Banach space, every Cauchy sequence has a limit point. So if you have that means if you have a Banach space B, and you have a sequence on it, and this sequence is Cauchy, since a Banach space is a space with a norm. A sequence is Cauchy if given epsilon bigger than 0, there exists an n such that for all n bigger than m, this is smaller than epsilon. So if this is the case, then exists x in B such that xn minus x goes to 0, so that is smaller than epsilon for all n bigger than n. So and this we write saying that lim of xn is equal to x. So what are examples of Banach spaces which are, right? For instance, any finite dimensional norm space Rn or Cn are complete. Why? Because essentially R is complete, and we are going to discuss a bit why R is complete in what sense. So the plane, for instance, is complete. There is no hole here because it's a vector space. So there is no hole. So if I have a sequence which is Cauchy, it has to converge to some point. Another example, which is infinite dimensional, is the continuous functions in an interval and then the norms sup. So we take an interval, compact interval of the real line, and look at all the functions which are bounded in this continuous and bounded in this interval, anything, and this set is complete. So the norm here is you take the norm of f in C of AB is the maximum of x in the interval AB of the absolute value of the function. But you keep, here you could put a non-continuous function, but you require that the space is of continuous function with this norm. And this space is complete. We are going to show that in a moment. Other spaces which are not complete, for instance, if you take all the functions in this the same interval, all the functions, and the norm now is the L2 norm, which is the square root of the integral between a and b of f of x squared. This space is not complete. Why? Because, for instance, you can take a sequence of functions that go like that. This is one, the next one is a bit like, let me draw it bigger. You can take a sequence that goes like that, then goes like this, then go like that, etc. So this sequence, you can check it's Cauchy. Why I know that it's Cauchy? Because the difference between this, say, and this one is just basically the area here, and this quantity is going to 0, right? So it's Cauchy. And nevertheless, this will go, the limit one here is going to be this function, which is non-continuous, right? So this is not the set of continuous functions, and this norm is not Banach. Can we make it to be Banach? Suppose, okay, we say, okay, let's try with non-continuous function. Let's allow this function to be here. But as soon as you allow this function to be here, this function, which is everywhere 0 except at one point, is also there. But then the integral of this function is 0. The integral of this is 0. So then this is not a norm, because there is an element which is not 0, but whose norm is 0. This quantity is 0. So this is no longer a norm. You can say, okay, is there any way out of that? Yes. You say, you will take the functions, the continuous, the functions, simply not continuous. So you take the space of all the functions under this norm and divide by some equivalent relations. And the equivalent relation is that f minus g norm is 0. So f is equivalent to f to g if the difference is 0. And so this is an equivalent relation, and this is a vector space, so this thing is a vector space. And now this is a norm, because this function is equivalent to 0, right? This here is equivalent to 0, so it's okay. It's just a 0 function. So basically, this is not true, but basically, the Banach space of functions in L2 is no longer functions, it's this equivalent class, and it's about this. So since here are not are not functions, because when you say, okay, what is the value of f of x? This is an element in this space. I don't know, right? Because since at some point I can put any value and it's equivalent to any other one, which are the same in all points. For instance, if we ask the function 0, what is the value of f at x? I don't know, because this other function is also equivalent to 0 and has some value which is not 0. So it's really not a function. It's some equivalent class. We will see now how to deal with these things. Here we have some spaces which are complete. Some more examples. This small L2 is a space of infinite sequences with the norm, the square root of the sum of the square of the components. So all the sequences where this norm is finite is a vector space and is complete. We are going to check this, or maybe it depends on the time. Otherwise, there is a proof on the nodes. The vector space L infinity, small L infinity, is a space of infinite sequence with the norm supremum. So the norm, you look at the maximum value of this thing, and this is the value, the supremum of that over E, over I. So this is called the space of all bounded sequences. These are Banachs. This is also complete. The one we saw before, the vector space of continuous functions in an interval with the norm, the supremum of fx in the interval. And this we are going to check that this is complete, because we are going to need that. For instance, a space that is not complete is the following. So this is the space of sequences x1, xn, such that after some finite number of elements is 0. This is a vector space, because if you sum two of these things, the sum also will have the property that after a while is 0, right? So it's a vector space, and the norm is this one we have here. And this space is not complete. Right? Why? Because, for instance, if you take the Cauchy sequence, which is 1, 1/2, 1/3, everything, so 1 over n, and then 0, and take another one, which is the same up to 1 over m. The difference goes to 0, because the differences are these numbers here, right? is the maximum of that, so it is 1 over n plus 1. This is the norm of the difference. We assume that m is bigger than n. So this is Cauchy, but converges to the sequence xi, which is just 1, 1/2, up to infinity, 1n, 1 over m, etc. So xi is 1 over I. And this one is not in the space because it has an infinite number of terms. So this is a case of a space of sequences with norm which is not complete. If you complete it, you get the L infinity. This one. Questions? No question? Let me. Okay. So now we are going to prove that the space of bounded continuous functions is complete. This we need because to prove that the solutions to the ordinary differential equation exist, we need to use this theorem, because basically what we are going to get is a Cauchy sequence of approximations to the solution, and we need to know that the limit exists. So we have to go through this proof. So we start with some sequence which is Cauchy in this space. So we have these are continuous unbounded functions, and being Cauchy means that if I take the norm of the difference, which is the norm, the supremum of the difference of the function, this is less than epsilon. So that's what we have. So we have let's draw something here. This is the interval. This is a member of the sequence, and this is another member, say, and they are converging, right? Because since this sup is going to 0, that means that if I take any x here, the difference for fixed x goes to 0, right? Because since the supremum is less than epsilon, for every individual x, we have this property, right? That means that we have for given fixed x, we have a sequence fnx of numbers, real numbers. So we have this sequence, and this is Cauchy at fixed x, because this difference goes to 0. So this should converge to a limit thing, a limit value, and this value we call f of x. So for every x we do this and get a function. So we assign at every x this number, which is the limit. So now we are going to see the properties of this fx, and in particular we are going to see that the sequence converges to this fx. So for doing that, we take in the norm that we have the difference between ff, fx, and fnx. And this is equal to the supreme here of the limit of n going to infinity of that. Why I can put the limit here inside this supreme? Because we are taking the maximum value, so I can put the limit, right, without any problem, because we are taking the supreme. So imagine I put this one here and I take the limit, the supreme over all x and n, so then I can, since I'm putting the supreme over all n, I can put the limit also. And that's what we do here. This is a supreme over all n bigger than n of the supreme of all x in this interval of this difference. But this difference is smaller than epsilon because n is bigger than n. So we have this. So given any epsilon bigger than 0, there is an m such that for any n bigger, any n m and n bigger than n, bigger n implies that this is smaller than epsilon, and so it also implies that this is smaller than epsilon, right? So the fn, the sequence, the Cauchy sequence is converging to these values for all x in the interval, uniformly for the same epsilon. So we still have to prove that fx belongs to the space. What it means? It's clearly bounded, but we need to check that it's continuous. So we have to check that it's continuous. Check that. So we take any point in the interval and we'll check that it's continuous at that point, and since this point is arbitrary, it's continuing the whole interval. So let's be epsilon bigger than 0, we choose it, and we want to find delta such that for all x minus y less than delta, this implies that fx minus fy is less than epsilon, continuity in the usual terms. So now we take n such that f minus fn is smaller than epsilon over 3, and this we can do because fn is converging to f, and delta such that fx minus fy smaller than delta implies that the function fn is smaller than epsilon over 3. And this we can assert because fn is continuous, right? So this we have. But then for any xy less than delta, we have fx minus fn, fy, we can write this as fx minus fnx plus fnx minus fny plus fny minus fy. And now we use a triangular inequality in this three pieces, this one, and this one, and so we get this inequality here, and since each one is smaller than 1 over epsilon over 3, we have that this thing is smaller than epsilon, and so we have continuity. Since f is continuous and the interval is compact, we know that f is also bounded, and therefore, because that's what we use for in the topology, that the thing we prove in the theorem we proved when we were looking at topologies. So we know that this function is bounded. So it's continuous and bounded, and so belongs to this space. And so the space is complete. Is it clear? Yeah? Okay. So we are going to use it in this result next week to prove that the ordinary differential equations have solutions for some time. And we are going to use this. So now we are going to talk about this theorem, which is very important. And this theorem, I will not give the full proof, but you can find it in a book by Yoshida. I think it's in the references. It's a nice subject, and the proof is not difficult. It's a bit longer, but it's okay. So, and the theorem is very important. It says, okay, suppose you have a normed space. And think of that as, suppose you have the rationals, and the norm is the absolute value. Think of that case, but it's general, of course. And so this, then there exists a Banach space with some other norm, let's call it B. A Banach space B and a continuous map from W to B with the following properties. The maps the norms one into the other. So it's an isometry, sense vector to the same norm. And phi of W is dense. As in B. This is a subspace of B in general, and it's dense. That is, if you take the closure, you get B. So in a sense, this is a space which is complete because it's Banach, and it has incorporated all the holes that this space has. If you think in rationals, you have all the rationals, and you have the irrationals are numbers also, real numbers, And so when you get this Q and do this operation, here you get the reals. So it's a way of filling all the irrationals into the real line. And the way it works is the way really that one should think about the numbers, the real numbers. So how it works? Thinking again in the irrationals, so you have a square root of 2. And you know that there are sequences of rational numbers one that approach this in the limit. Of this sequence. And this sequence is Cauchy. And you might say, okay, well, I know that this number should exist because this is the result of the longitude of the diagonal on a square of side 1, right? So you have in mind that this thing exists. And so it's a sort of natural thing, okay, this is a number, because I should be able to measure this. But in general, there could be many things that do not have an interpretation so easy as that. So how do we incorporate all the real numbers, all the irrational numbers? And okay, you can say, okay, I'll do this space, a big space of all Cauchy sequences. So take all the Cauchy sequences of elements of Q, of W. Right? So these are things Wi. Now this space is too big because I can find many sequences, Cauchy sequences that approach square root of 2. And I am only interested in this number, not in all the Cauchy sequences. So I will say, okay, we'll quotient this space, and there are equivalence relations. And we will say, okay, a sequence is equivalent to another sequence if limit n going to infinity of xn equals limit n going to infinity of x tilde n. So we will consider all sequences to be equivalent if they actually this is not the right way of saying this. Sorry. Because I don't have the limits. Each individual limit, sorry. If I say if the difference goes to 0, so if the difference goes to 0. So they actually, so you have a sequence, say, going here, and a sequence going here. And these are equivalent because they approach each other. So then we say they are equivalent. Now, if these sequences are approaching something, then the limit of this sequence is going to be equal to the limit of that sequence. And so we will have this relation. But if there is no point, then the elements there were not approaching anything are new points in my space. So this space is going to be B. And what is a map phi? I need to introduce now the map phi. So this space is a space of sequences with these equivalent relations. and I need to introduce this map. Well, given an element here, the map just gives me the sequence X, X, X. And the class equivalent, the equivalent class of this sequence. So you take the equivalent class of this sequence, and this is the element here. And this is what you have to show now, is that this is dense. This map is dense. And also that this space, the space of Cauchy sequences with this relation are complete. And this is done in this paper by Yoshida, in this book. So it's not difficult, you can follow it. So this way we complete the spaces. So given any vector space, W with some norm, we transform into a Banach space just by completion. So think about the number. This says, okay, numbers are not really, the real lines are not really quantities, but they are Cauchy sequences and are equivalent class of Cauchy sequence. So if I have two sequences approaching pi, in the sense that pi exists, then they are equivalent. And so pi is actually the set of all these sequences approaching each other. This is what is the number pi. We think of pi as a number, but it's actually this construction. So the real numbers are not quantities that we can assign a value, but they are just Cauchy sequences. The rationals have values, the irrationals you can approach as much as you want. Oh. ¿Volvió?